Time is 2:30, so let's begin. So project number 1, I've moved the due date to class time on Thursday. One reason why I did that is because unfortunately I did not go over problem number 3 yet on the project, and I wanted to talk about that at least briefly in class before you guys turned it in, and I forgot to do that last time. So that's one reason why I decided to move it back. Now, project number 2, I hope to give it to you on Thursday, but to be honest, it's not looking like I'm going to be able to. This snowstorm kind of screwed up my schedule, as maybe it did yours, because I was hoping to write it on Monday. Unfortunately, I wasn't able to. So we'll see if I can get project number 2 out to you on Thursday too. So today, what we're going to do is begin by talking about problem number 3 on project number 1, and also I'll ask if there's any other questions about the project at that time too. Then we will continue in chapter 2. So are there any questions before we start talking about the project? Also, I guess I do want to bring up, notice test number 1 is 2 weeks from today, so be prepared. Also remember with test number 1, I have given you test number 1 from last year as well. And what I recommend that you do is maybe after Thursday's class, try to take test number 1 and test conditions similar to what you would have here in terms of you'll be using a computer to do stuff and only have access to my programs. Okay? Okay, so let's talk about the project. So I came across this data set a few weeks ago. I thought it was interesting, so I decided to use it for this project. And had anybody heard of Olestra before as a fat substitute? Okay. So, you know, where you may have run into it, at least where I've run into it, is what were called wild potato chips a number of years ago. I remember when they came out, it was late 1990s, I thought, oh yeah, I like potato chips, and if I don't have the calories with it, that's great. Then I tried them. They tasted good. But there were some side effects. And I decided never to eat wild potato chips again. And so anyway, other people have complained about side effects as well with eating foods that had Olestra in it. And so this led to some research that was done, in particular a paper that was published in the Journal of the American Medical Association that did a controlled experiment to see if, well, if people ate regular potato chips or the potato chips with Olestra, was their amount of side effect, was if they would have a particular kind of side effect, was it different? Or I should say, let me restate that. Is the probability of having a side effect different for these two essentially treatment groups? And so this is the data that some of the data that they had collected here. So for example, 89 people who ate the Olestra type of potato chips did have side effects, but 474 did not. And so using this data, what I would like you to do is answer the following questions. So part A here asks you to go get the paper. So you can download it from the library's website, and take a look at the first few pages of the paper. And based upon what you read there, tell me what exactly was the sample that was used. Also then tell me, well, what's the population that you're trying to extend the inferences to? So this gets back to what stuff that you would have learned like in a Stat 801 course, where you have a population of interest, you take a sample from the population, and then you try to make inferences from the sample back to the population. Tell me what the population is. Tell me if there's any assumptions that one would need to make in order to use this sample to be representative of the entire population. Okay. Then part B asks you to do essentially the numerical calculations. Do a Pearson chi-square test. Do find the relative risk and the corresponding, find the estimated relative risk and the corresponding confidence interval. Also do the odds ratio as well, the confidence interval and the estimate. And just so that everyone's using the exact same level of alpha here, let's do alpha 0.05 for your tests and confidence intervals. well, if I know one was using an alpha equal to 0.01234, and I'm now having to change what we've done in the past. So now normally one would only do, let's say, one of these, maybe two of them. You wouldn't necessarily do all three in actual practice, but I want you to get practice in being able to do the calculations and interpret the calculations correctly. Now, in your write-up for this problem, I do want to see statements such as the odds of having a side effect are such and such times as large as such and such, or a particular number times as large for the Elacer group in comparison to the regular potato chip group. I want to see statements like that. I do not only want to see, let's say, OR hat is equal to 9, and you don't say anything else. Okay? So the numerical calculations, they need to be done, presented, and also the correct interpretations need to be given too. Any questions about that? Yes?
Do we interpret also for the confidence intervals for the RR and the OR as well?
Well, that's part of a full interpretation. Yes. Now, part C then says, okay, well, based upon what you found out in B, and I guess one way to check your answer, whether you do a Pearson chi-square test for independence, a relative risk or odds ratio, you're going to come to the same conclusion. Okay? Now, based upon your conclusion, answer either I or double I. So, for example, if there is not sufficient evidence that Elacer caused side effects, well, then tell me, why could that occur? If people have reported side effects, tell me a statistical reason why your conclusion is not the same as what maybe other people are saying. Yes, there's a problem with this. A statistical reason. I would expect something from your Stat 801-like class will lead you to a conclusion, or an answer, I should say. Then part D. So, so often in the news media, you're going to hear reports about, hey, there was a new study done, and such was found to cause a disease or do something. Well, what I want you to do is write up what will be like the media report, reporting the results from this this study in terms of what we're looking at in the study. There was more other stuff that was done in the paper, but just focus on like the table results that we got here and also your results in part B. Write up a one-paragraph report that will be appropriate for like a newspaper like the Lincoln Journal-Star. Just realize that the people who read the Lincoln Journal-Star, not all of them had a stat course before. So you need to take that into account when you write this up. Are there any questions? So that's problem number 3. Are there any questions about problem number 3?
So just to be sure, for part B, when we calculate the statistic, we also need to include the confidence intervals for the journal.
Yeah, because you can't make inferences about the population without the confidence interval. Because it comes down to, if I just say OR hat equals 9, how do you know you're not going to get 1/9 the next time you run the experiment? That's the whole purpose of doing statistical inference, and have a certain level of confidence associated with what is the true parameter value. Any other questions about number 3? Okay, were there any questions about number 1 or number 2 that anybody wanted me to address?
I have a good question.
Sure.
So for number two, when you use the binomial confidence function to calculate confidence interval in letter A, can that be used in letter B as well? Because you mentioned at the beginning of the question, when you say 2 up there, you say do not use binomial plot, just the plot. It's fine.
Yeah. Well, I'm hoping to make it easier that you will use binom.confident for B.
Yeah, that's what I did.
Just not the plot.
For question 1,
Okay.
where we're supposed to calculate the confidence interval for the 4 different confidence intervals.
Yeah.
Can we just use that
if you want to use that simple of function, you can. Just make sure that you know how to do it without it. Okay? Because I know obviously that makes it a lot easier. You know, I have thought about, you know, just using only that function in class. But you know, as I've said, I think I even said in class, I found errors before with that function. It wasn't calculating stuff correctly. And so I kind of feel more better about it when I do my own calculations rather than rely on that function. And plus, also there's a learning experience with how to use R, especially at the beginning of the semester, by actually programming in the equation yourself. So it's up to you which one you want to use, but just make sure that you understand how to use it without the binomial, how to do the calculation without binomial.confident. Does that make sense? Okay. Other questions?
Question 3, the first one. The sample size in the paper, the age is between 13 and 88. So
Yep.
I'm not sure in population you need to use the whole range.
Well, that, you know, and that's kind of what I want you to address. You know, obviously there are limitations about what you can do in terms of a sample, but despite those limitations, often we want to extrapolate farther. So I'll give you an example. The beginning of section 1.2, I gave, I think, 4 different 2x2 tables. One was for an HIV clinical trial. That clinical trial was done in Thailand. But what, of course, I would expect that the researchers want to do is extrapolate the results beyond people who are, let's say, living in Thailand to the whole world. Well, but Thai people were the only ones that were in the sample. And so what's an assumption then that you have to make? Well, those people were representative of all people in the world. You know, despite maybe there are some genetic differences that maybe would make them more or less susceptible to HIV. Those are the kinds of things that you need to take into account, just as a researcher would, for trying to make inferences about a population.
So you mean both works just as long as you make an appropriate assumption?
Perhaps. Okay. I mean, I could see perhaps more than one way to answer the question. I think there's going to be more. I think there's going to be one answer in particular that will be best, that I hope you will find. I think of it this way. So, with these wild potato chips, who could buy them? Well, you might not ever had an experience where you saw wild potato chips in a grocery store, but anybody could have bought them. And maybe parents buy them and they give them to their kids. I hope not. That would be a big mess. But they could give them to their kids. Okay, so what do you think maybe the population intent was for this clinical trial? Or not clinical trial, but this experiment. Okay.
You won't give the potato chips to babies under 1 year old?
Well, that might be a little bit more difficult for them to eat. I mean, I wouldn't give them any kind of potato chips to babies that old. Maybe at least 2. Then again, don't give them potato chips at all, and they'll probably live a happier life. But yeah, those are the things that you need to think about. Any other questions?
Since we're working in groups, can we just submit one?
Yes. Yes, please. Please only submit one. Anybody eat wild potato chips before? Well, good for you. Okay, let's move on. Let's see now. So we left off last time, page 212. So we were talking about this data that I collected, this place-kicking data set. And we have 1,425 observations. And what we like to know eventually, as we move on to chapter 5, is, well, what factors affect the probability of success for a place kick in the NFL? Look at my sample here. It was 1995. What would be my population, do you think? Or my sample was all place kicks in 1995. What do you think my population would be? You think it from a coaching standpoint. What would I like to do with this data? Suppose the year was 1996. Would I want to try to use this data to help me out in maybe a game? To make a decision about what to do? Well, yeah. So what's my population? Well, obviously, population has to include the sample, 1995. But my population might be 1996 as well. How about 97? How about 98? How about 1999? What kind of assumptions do I need to make, though, in order for this to work out? And will my sample from 1995 now carry forward to 2014? Can I use that? What assumptions would I need?
Constant for the price for a particular distance is the same across the years.
Well, the distance is the same across the years.
The probability of success doesn't change.
Yeah, but in order to do that, what do I need? What assumptions do I need? Whenever we make an assumption, whenever we make an inference from the sample to the population, you need the sample to be representative of the population. So what we need, in order to guarantee what you were saying, is that we need 1995 to still be representative of 2014. For football fans out there, what do you think? Has the game changed at all? Has field goal kicking changed at all in 20 years?
Yep.
How?
I don't know, which probably change.
Well, okay, so what would you look at? Well, have there been rule changes that have affected the probability of success of a field goal or PAT? I don't think so. There's been talk about, in terms of PATs in football, if you're really into football, you've probably heard about this, maybe we should, instead of having essentially a 20-yard distance, maybe it should be 30 or even longer to make it more challenging. Well, that hasn't happened. But if it did, well, shoot, what can I do with my model now? Maybe I can't use it because some rule changes have changed how football is played. But as long as there's not those rule changes, or maybe there isn't like a dramatic discovery of a new kind of shoe that allows kickers to kick the ball, let's say 50 yards longer or even 10 yards longer, probably my data here is still going to be representative of football now. And so I can use my model. I think the one big change that has happened is the playing surface. Because back in '95, if you had artificial turf, basically the artificial turf would be like as smooth as this carpet here. Now you have artificial turf like what you have in Memorial Stadium, that it's basically like artificial grass blades. So the artificial turf has changed. Has that really affected, though, the probability of success for a place kick? I don't know. If it did, maybe it's probably very, very, very minor. But those are the kinds of things that you need to consider, when you're thinking about what's my population of inference.
Sorry, even if there doesn't change, how would that be a problem?
Well, let's say, let's say there's this new shoe out there that allows football, the kickers to kick it 10 yards longer. Okay. Well, that means, at least with respect to the longer place kicks, they're going to have a better chance of making them now than they did before. That's why.
But it's still part of the population.
Excuse me?
It's still part of the population. We will just need to model the population.
No, because in 1995, when I took my sample, those kinds of shoes didn't exist. They didn't have access to them. And so because of that, the abilities of the place kickers have essentially changed. And so, so 1995 would basically form a different kind of population than it would now. Okay. You know, think back, if you're a big football fan too, back in the 1960s, I think this happened when they moved the goalposts. Before they were at actually the goal line, now they're at the back of the end zone. Well, obviously, if I had data from the early 1960s, I couldn't use that for let's say the 1970s. And in fact, I'm really getting into football here. You know, back in the 1960s, I think even in the 1970s, the way that place kickers used to kick the ball was they would go straight on and try to kick it with their toe, with the front of their toe, rather than the soccer style place kicker that place kickers do now, where they do the I guess the inside of their toe right here, or inside of their foot, and that has brought the ability of place kickers to kick it farther and to have more control over it than what they did before. So I couldn't use data that where place kickers used to kick it head on to now predict to predict today, I should say. Okay, enough about that. So my data is in a file called placekick.csv. It's a comma delimited file. And so I use the read.table function to read it in, where I say SEP for separator equal quote, comma, end quote. I could also use the read.csv function. That would be easier. I just decided to show you a more general approach. But read.csv would work just fine. And I used the head function with the Placekick data so that you can see what the first 6 observations look like. So again, I have week of the season, distance in yards of the Placekick, change is a measure of pressure, elap 30 is the number of minutes left to go in the half. PAT is a binary variable, 0 for field goal, 1 for for point after touchdown. Type corresponds to, is it a dome stadium or outdoor stadium? You know, I guess one thing that has happened since 1995 when I collected the data, another thing I should say, is that there were no retractable roof stadiums back in 95, where there are now, like, for example, for the recent Super Bowl. The field was it grass or artificial turf? Wind, was it windy or not? And then lastly, the good variable is our response variable, 1 for success, 0 for failure. This is a Bernoulli response. We're going to focus on the distance explanatory variable for now. And so this is the model that I want to estimate here. Remember what logit of pi represents. It's like a shortcut way to say log of pi over 1 minus pi, where pi is my probability of success for the place kick. So again, what we're modeling here is the log odds of a success. And we set that equal to a linear combination of my regression parameters, which are my betas, and my explanatory variables, which are represented by my x's. In this case, I'm only going to have one x, which is going to represent distance. It's okay with me if you want to write the model a little bit less formally by not including x in there, and instead using the word distance. That's okay with me. So to estimate the model, I use a function in R called GLM. We talked about GLM, the letters GLM last time. GLM stands for Generalized Linear Model. So linear model will be like the regular old normal linear regression models that you've all seen prior to this class, and of course like Study 01. G stands for generalized, because now we are generalizing what these models can do for us. And this is how you use the GLM function. This is actually in the stats package, by the way. You first state your argument formula, which tells R, well, what model do you want to estimate? Formula works the same way as it does in the LM function that you saw in the intro to R video. And the response you put first, good, or you can say your Y variable. And then you separate the response from the explanatory variables by a tilde. And then we only have one explanatory variable, distance. My data is in the data frame called Placekick. And then lastly, the family argument says, what kind of generalized linear model do I want? As you will see later in chapter 2, there's many different kinds. What we're interested in is for logistic regression. And this is how you specify it. You say family equal binomial. And remember, I have a Bernoulli response here. That's where basically binomial comes from. And then I have to specify within parentheses then, how am I relating this linear combination of the betas and the x's? How am I relating it to pi? Well, remember, I'm using this logit function to do it. Logit mathematical function. So I put as the link how I'm linking the two different components together by logit. There's other ways you can link them too, and again, we'll find out about those towards the end of chapter 2. So this is how I estimate my model. I put the results into an object called mod.fit, and then I simply type mod.fit to get a general idea of what's in there. This is what I get. Okay, so this is on page 214. I guess 213. Let me go over there. So underneath coefficients, remember how essentially these betas are coefficients on x's. Underneath where you see distance, that is my beta hat 1. So this is the maximum likelihood estimator of beta 1. Yes, there is a difference between beta hat 1 and beta 1. One's an estimator, one is the parameter. Where you see intercept, well, that's essentially like the y-intercept of this equation, and this is my beta hat 0. We'll talk about some of the other stuff that's given to you there as we go along in chapter 2. So using that information, then, this is how I write out my estimated logistic regression model. Notice that I have a hat on top of pi. I need that there because this is the estimated model, not the true model. And if you don't have a hat there, every time I will take off points. You know, it's just the difference between an estimator or statistic and also a parameter. Okay, so that's my estimated model. So tell me, describe to me the relationship between distance and the estimated probability of success. As the distance goes up, does the estimated probability of success go up? It goes down. Why? Because of this right here. It's a negative sign. So as distance goes up, estimated probability of success goes down. And if you're a football fan, you know that's to be expected, because the farther you are away from the goalposts, the more difficult it's going to be to make the kick. Now this mod.fit here, you saw me use kind of a similar syntax in the Intro to R video. And when we did this with the LM function, we put the results into an object called mod.fit. And there was actually a whole bunch of stuff that was actually stored in there. In order to see what's stored in there, or get a listing of what's stored in there, you can use the names function. So if I say names mod.fit, I see a list of about, maybe about 30 different items that are actually stored in there. Just they weren't all printed off when I just typed mod.fit. So in order to access these items, that's where that $ comes in handy that you've seen before. So if I say mod.fit $ coefficients, notice my coefficients in this list of items up here, I get my beta hat 0, and I get my beta hat 1. Any idea what fitted.values will be?
Predicted.
The predicted values. In other words, this is going to give me all my pi hats for I equal 1 to 1425. So like in a normal linear regression sense, this would be like your y hats. And again, there's a lot of stuff in there, stored in there. We haven't talked about it all yet, so be patient. We will talk about most of the stuff that's in there as we go along in chapter 2. Let's say that I only wanted to pull out just beta hat 1. How would I do that? Just a second. How would I just get beta hat 1 only? What would I need to do? Like that. So I get the second element of what's in mod.fit $sign coefficients. We will be doing that shortly. Because basically what this is, what R is representing this as is simply a vector. In other words, it's putting all these beta hats together into just, I guess, I don't want to say the word vector. It's kind of like with the C function, where you combine this stuff together. It's the same kind of thing. What was your question?
Yeah, the mod.fit, that's just the name you chose. That could have been any.
It's what?
The mod.fit, the object name.
Yeah.
That's just something you chose randomly. That could have been any.
I could have used a different name. Yeah. It's just, I chose it. I like to use mod.fit because it says model fit, essentially. But you could have called it something else. The key is, you can use periods in there, you can use underscores in there, but you can't just say mod and then a space fit. Now also, if you remember, we did this in the intro to our video. I can summarize the information that's stored in mod.fit. So I can say summary parentheses. If you wanted to be real formal, you could say object equal mod.fit, or you could just say summary parentheses mod.fit in parentheses. And this is what's printed. And so if you've ever, well, I think all of you have used, let's say, a statistical software package before to fit like just a regular old normal linear regression model, you often will see some summaries similar to this. And that's what the summary function gives us in R with an object that comes from GLM. So here we have, for example, beta hat 0. Here's beta hat 1. Under the STD period error column, what do you think that gives me? So let's say this right here. What do you think that is? This is standard error. Could someone tell me what that exactly means, just to make sure you understand that?
The standard deviation of the sample.
Yeah, the standard deviation of the statistic, or the estimator. So it's the estimated variance of beta hat 1 square rooted. How about you see this thing called z-value? What do you think that is? Suppose we do it for the distance row. It's a walled test. So it's negative 0.115 over 0.0083. Negative 13.79. If you don't know what it is right now, that's fine. We'll look at it hopefully today. We'll see. So it's a walled test, walled statistic, that actually allows you to test, is beta 1 equal to 0 or not? Using a normal approximation, we get a p-value of less than 2 times 10 to the negative 16th power. So, do you think there's a significant relationship between distance and the probability of success? Yes, there is. So, just as kind of a review of some stuff that was in the intro to our video. So again, when I do summary mod.fit, as we saw in the output, this is what I get. Now let's say if I do summary Placekick. Remember my data is in Placekick. Will I get the same kind of result? No. Instead, I get some other kinds of results, but it's the same function. Does anyone remember why that occurs? What?
It's a general
It's a generic function. Yeah. So summary is a generic function. There are many different generic functions in R. And what they do is, the first thing is that they check what is what's called the class of an object. So if I do class mod.fit, it actually has two different classes. One's called GLM and one's called LM, where the GLM would get precedence. And if I do class Placekick, it's a data.frame. So the way that R operates with these generic functions like the summary function is the first thing it does, it checks what is the class of the object. It finds the class of the object, and then it goes to another function called either summary.glm or summary.data.frame and executes that, because that particular function is specially then made for that type of object. So that's why R is called an object-oriented language. You can use this term, this wording such as summary. Plot is also a generic function as well. You're going to see a function called predict in this section as well. That's a generic function. And all those functions operate by first checking the class and then finding another function out there that's meant specifically for that class. And this is purposely done so that you can use the same common terminology, whether you're estimating a logistic regression model, whether you're estimating a normal linear regression model, whether you're estimating a Cox proportional hazard type of model, whether you're estimating a generalized linear mixed model, whether you're doing something else. You still use the same terminology: summary, plot, predict. The thing is, though, is for people who are new to R, who have never seen object-oriented languages before, that obviously can be a little bit confusing. Now, how do you know what's available to you in terms of like a summary.glm function? Now, a summary.glm function is what's called a methods function. And to see all the methods functions that are available to you, you can use methods class equal GLM. And here are them all. In particular, there's summary.glm. Excuse me. We're going to be looking at this one very shortly, called vcove. Okay, so let's move on to page 217. So this is another way that you can write out your estimated logistic regression model. You can put logit pi hat is equal to, then beta hat 0 plus beta hat 1 times x, or you can write it this way. It doesn't matter. It's exactly the same model. Now, though, we have pi hat only on the left-hand side. This is especially useful when you want to maybe actually do some predictions. So let's say for a distance of 20 yards, I want to find what will be the estimated probability of success. So all I do is in my equation, I put 20 for distance, I do the math, and I get about 0.97. How would we do this in R then? There's a variety of different ways. Here's one. Let me go over here to my program. What is that in my program? Sorry. Well, I know it's in my program someplace. I don't know where it is right now. Someone says scroll down.
It's at line 349.
Okay. Thank you. So what I need to do is I need to take beta hat 0. Remember, that would be now the first element of mod.fit $sign coefficients. I need to add that to beta hat 1, second element, times 20. And so if I do that, what I get is 3.51. And so if I take 3.51 with the exp function divided by 1 plus exp 3.51, I get 0.97. There's my estimated probability of success. You can do that a little bit more slick by, let's say, putting then that result, that 3.51, into an object called linear.pred. Why am I using that terminology? Well, if you remember from last time, this linear combination of the beta hats and x's, that has a particular name. It's called a linear predictor. So that's why I chose that terminology. And then I use the exp function then with linear.pred to get essentially the same result. Note that we have this odd label here called intercept. Well, where does that come from? Well, R, for some reason, decides to take the label that comes with this mod.fit $sign coefficients. The first element, notice the intercept? Since there wasn't any other label, it chose the first label that was presented to it. And so to remove that, it's just more of a thing to make it look nice, and so there's no confusion. You can use as.numeric. What that basically tells R is treat this as just as simply a number. And notice the intercept thing goes away. Okay. Let's see. So on page 217, then I also show what happens with a probability of success. I'm sorry, what happens with a distance of 50 yards. You get an estimated probability of success of 0.52. And based upon what we saw with the negative beta hat 1, this makes sense. The estimated probability of success goes down as distance goes up. Now let's use the same idea of how to find the estimated probability of success with the curve function so that we can actually plot the model. And so we've seen the curve function before. The key element in it is this EXPR argument, which stands for expression. So what I need to do is simply put in my mathematical expression as a function of x that gives me my pi hat. So I say EXP once again, I get my beta hat 0 plus my beta hat 1, I multiply by x. Divided by, then 1 plus that same thing. I'm going to specify limits of 18 to 66 yards. The reason why I do that is because the minimum distance in the data set was 18. The maximum distance was 66. I wouldn't want to go beyond that because that would be extrapolating beyond the range of my data. I put some nice grid lines on my plot as well, and this is my plot. So again, we can see as distance goes up, the estimated probability of success goes down. Any questions? We'll look at later, not today, but later. We'll look at this more closely later to determine, well, is this really a good fit? Is this really explaining? Is this really doing a good job of estimating the probability of success? We'll use some graphical measures to do that. Okay, so let's see here. Now let's say that you had more than one explanatory variable. Let's say that I want to use the change variable and distance. Well, it's easy to get them both in the model. All you do is you separate the two variables by a plus sign. That's it. It doesn't mean that they're being added together. It's just a way to say essentially the word and. I want change and distance. And my code is exactly the same as before. And this is what I get then for my results. So my estimated logistic regression model, which is shown on page 220, is this right here. So tell me about the effect that change has on the estimated probability of success. Remember, change basically represents a 1 for pressure, a 0 for no pressure. So tell me, what happens to the estimated probability of success if there's pressure? It goes down. It causes the estimated probability of success to go down in comparison to the situation where there's no pressure. Now, that's for the sample itself. We still haven't made judgments about the population, though. Again, that's where confidence intervals and hypothesis tests will be used to make that judgment, so we can say with a certain level of accuracy, yes, there is a pressure effect, or no, there's not. Yes?
Plot the model right now.
Well, if you were to plot the model right now, obviously now you have two x variables. And so what I would recommend doing is you fix change to be a 0. Okay? Plot that model. So notice it's just a function of distance. Fix change to be 1. Plot that model as well. Because again, it's just a function of distance. So what you'll have then is a plot that looks something like this. You know, perhaps this is for change equal to 0. This is not true, but let's say it is. And then for change equal 1, you're going to see something that looks like this. The reason why that new line is farther down is because, remember, there was a negative coefficient, negative beta half. And there will be some good plots later in the notes that demonstrate that. I'll just give you a page reference real fast, hopefully. Well, in chapter 5 there will be, I know that for sure. This will be actually a case study in my book, or is a case study in my book, and we'll look at change along with some other explanatory variables as well. There is an example on page 280 in the notes that shows what happens when wind is in the model too. And we have what's called an interaction term. Now, it's great that we have this GLM function, because otherwise what would we have to do? Well, we would have to program in the likelihood function ourselves. And then similar to what we did with that very simple field goal kicking example in section 1.1, we would have to put a whole bunch of different values of beta hats into the likelihood function and look at, well, which ones actually make our likelihood function as large as possible. Okay, that's how we would do it if we didn't have the GLM function. Well, in my book, I actually talk about that kind of, where instead of using the GLM function, I essentially do that, but I also take advantage of a very, very, very useful function called optim. And optim basically allows you to maximize or minimize any kind of function you want. It's a really cool, any kind of mathematical function you want, I should say. It's a very cool function. Take a look at that in my book. Unless you hear from me, otherwise, though, I want to ask you a direct question on it, on a test or a project. Let's talk about the variance-covariance matrix. So we got these beta hats now. We want to understand their variability because they're not going to be the same for every single sample. So in 1996, I wouldn't expect my beta hats to be exactly the same, even if 95 and 96 were representative of the same population. This is a different sample. And so what we can do is that we can look at what's called the variance-covariance matrix for the beta hats. And this is the form of it. I would expect that most of you have seen a variance-covariance matrix before. Just in case you have not, this is the structure of it. Notice there are rows and there are columns. So if you notice here, there will be p plus 1 rows, and there will be p plus 1 columns to this matrix structure. So the row 1, column 1 element is the estimated variance of beta hat 0. The second row, second column, is the estimated variance of beta hat 1. The first row, second column is the estimated covariance of beta hat 0 and beta hat 1. You remember what a covariance represents is the dependence between two different items. Okay? It's very closely related to the correlation. And so this is when I put everything in this form, this is a matrix. And since you see the vars, you see the coves there, that's why we call it a variance-covariance matrix. Just to simplify things, I'm just going to call it a covariance matrix. Okay? And so what this again is representing is the variability that we have in our estimates, and also the dependence that we have amongst our estimators. Note that a variance-covariance matrix is what's called symmetric, meaning what's above the diagonal also appears on below the diagonal, where the diagonal is this right here, where the row number and the column number are exactly the same. So for example, let me actually use a highlighter. So what I'm highlighting here in yellow they're the same. If you want to know more about covariance matrices, more than what I'm talking about here, take a look at my Stat 870 notes. That's the regression course that we teach on campus. Download it from my website, all my notes there, and you'll see more of a discussion of the variance covariance matrices. Okay, well, how do we find this covariance matrix? How do I find the estimated variance of beta hat 1? How do I find this one of the covariances? Well, it all goes back to what we learned about in section 1.1 with likelihood-based methods. And that was if I had just simply a maximum likelihood estimator, call it theta hat, that has an approximate normal distribution to it. So if you notice how I use a tilde, a little dot on top of it, that means approximate. Theta hat has an approximate normal distribution to it with a mean of theta and a variance of estimated variance of theta hat. Or in other words, it's this thing that's dependent upon the second derivative of the log likelihood function. Okay, so that came from section 1.1. Now, we still have maximum likelihood estimators, these beta hats. And so now we just need to talk about the extension of this from, let's say, 1 dimension to p plus 1 dimensions. Essentially, I don't like that wording. From one statistic to p plus 1 statistic. So from 1 estimator to p plus 1 estimators. And that extension, let's take a look at it in terms of if you just have beta hat 0 and beta hat 1. This is the extension. We're still working with the log likelihood function. Now we're taking second partial derivatives. You're still taking an expected value. You still have an inverse. You still have a negative sign out there. And you still evaluate the parameters at their estimates. This would be the estimated covariance matrix for beta hat 0 and beta hat 1. And you'll have to do this by hand. That's a joke. R is automatically going to do all the calculations for us, but this is what's representing. It's still good for you to know what it's actually representing. If you've had a course like Stat 870, let me relate this to something you saw in Stat 870. Basically, and I'm not going to ask you this part now on the test. Basically, this matrix for logistic regression is actually x prime vx inverse, where x is your usual matrix of your explanatory variables with a leading column of 1s. Sometimes people will call it a design matrix, for example. And v is a diagonal matrix with the Bernoulli variances, estimated variances, on the diagonal. And this all comes about through what's called weighted least squares estimation. It's exactly the same covariance matrix. If you've not had matrix algebra, you haven't had Stat 870, don't worry about it. I just like to still relate, for some students who have, I know there's a number of students who have, relate what we're doing here to what you've seen in another course. Okay, so let's talk about how R then calculates for us this estimated covariance matrix. Simply, remember what I showed you earlier for that method function, vcov.glm? Well, we can use the generic function vcov to find the estimated covariance matrix. So all I do is I take my object from GLM, mod.fit, I put that in vcov, and this is what we get. So for example, right here is the square, I'm sorry, not the square root. What we get right here is the estimated variance of beta hat 1. This right here is the estimated covariance of beta hat 0 and beta hat 1. Now earlier, when we had our summary on mod.fit output, remember how this right here was the square root of the estimated variance of beta hat 1. So if I square 0.008337, I will get this 6.95 times 10 to the negative 5th power. Okay? Any questions? Yes?
That would be the standard error that we saw earlier on.
This right here is the standard error. Okay? And also to make sure that this is clear, let's say that I wanted to extract one element of this matrix here. The way that I can do that is to use this bracket notation that we've seen before, where I say I want the second row and I want the second column, if I can spell it. That's how I can extract it out of the matrix. We will need to do that kind of stuff later on when we do some confidence intervals for odds ratios, for example. Any other questions?
For the notation, I notice you have add on the variance and add on
The hat,
so
yeah.
Do you have to put that, would you penalize if you don't put add on the variance?
Well, I think you're trying to get at this. Are they equivalent? No, they're not. This one will be dependent upon parameters. This one will not. So to put it in terms of section 1.1, what we learned there, the variance of pi hat is pi times 1 minus pi over n. The variance hat of pi hat is pi hat 1 minus pi hat over n. That's the difference. Also, I think it's good to bring this up to relate to something that you would have in your first stat course. Let's say that we have a sample mean x bar. Okay, what's the variance of x bar? Sigma squared over n. Does that look familiar? Often you talk about it right around the central limit theorem. Well, what would be var hat x bar? You could say sigma hat squared over n, or equivalently, often we use the letter s to be the sample variance, s squared to be the sample variance. That's the difference. And we're just showing that now in terms of beta hats. Okay. So now that takes us to page 24. So sometimes you might observe your data in terms of the number of successes out of a particular number of trials, rather than either it's a success or a failure. So with the place-kicking data, we observe our data in a Bernoulli format. But there are times when you might observe the data so that you have, let's say, 5 successes out of 9 trials. Then next time you have 4 successes out of 8 trials. You can still work with that kind of data. And your answers, whether it's a Bernoulli format, or a binomial format, as long as you have the same number of successes out of in terms of same number of successes out of a certain number of trials, will always be exactly the same. Let's talk about then binomial data with more than one trial then. Let's say we actually observe these W's. So W1 is the number of successes that we've had out of N1 trials. And we observe also W sub J, which is the number of successes out of N sub J trials. So very similar to what we saw in section 1.1 and 1.2. So instead of having essentially a sample size of N, we have a sample size of J. J different binomial observations. Then this is what we're still interested in, though, in estimating the probability success parameter. So this is what our likelihood function looks like in that situation. And it's almost exactly the same as what we saw before, except for we have this combination there. And instead of having y's, we have w's. Okay? We can find the log likelihood function. And this is what it looks like using properties of logarithms. And then to find the maximum likelihood, and remember what this pi would be. Oops. Remember what this pi would be in terms of our logistic regression model. Let's say we have just one explanatory variable. Okay? So we want to find, let's say, maximum likelihood estimates of beta 0 and beta 1. What would we do? Well, if we were to do this by hand, if we really wanted to, we would take the derivative with respect to beta 0, set it equal to 0. Take the derivative with respect to beta 1, set it equal to 0. Try to solve for beta 0 and beta 1. And you actually would have to use a numerical iterative method to do that. But notice what happens when you take the derivative with respect to beta 0 or beta 1. What falls out of those terms there? What becomes 0? Does this become 0? If I would take the derivative with respect to beta 1, it would be messy, right? Kind of. But would it be equal to 0? How do you get a derivative that's equal to 0? For those of you who've had calculus, which I would assume is most of you. Constant. Okay. Do you see any constants up there? A constant would be something that's not a function of the betas. What's not a function of the betas? Right there. So notice how that falls out. And now, hopefully you can see how the derivatives with respect to the derivatives of the log likelihood function will be equivalent, rather if you're working with binomial data or Bernoulli data. They will be equivalent. Relate what we had earlier in the notes last time to what we have now, and you'll see that. So now let's take a look at how we can estimate the model when we have the data in this format. And so what I need to do, first of all, is have some binomial data. An easy way to do that in the context of the place-kicking data set is, let's find how many observations had, let's say, a distance of 18 yards. Count the number of successes. Let's go to 19 yards, do the same. Go to 20 yards, do the same. And now you have binomial data. And so that's what I did. So we'll be using this function a number of times in Chapter 5. This will be the first time, though, that we'll see it. What we're trying to do is essentially aggregate my data. We're going to try to aggregate the data over distance. So we're going to try to find all observations that have exactly the same distance and aggregate it. So I'm going to use a function called aggregate to do that. And I'm going to aggregate it this way. I want to summarize all the values for good. Remember, that's my success or failure by distance. There's my data, Placekick. And how do I want to summarize it? I want to sum up all my 1s and 0s that are in good. So let's go ahead and do that. Put that in an object called W. And this is what we get. So at 18 yards, there were 2 successes. At 19 yards, there were 7 successes. Now let's find what the number of trials would be at each distance. So I have exactly the same code, except for I have length there, which basically counts how many items I have. I put that into an object called n. Then I'm going to create a new data frame, w.n, that contains all my distances. So I pull out my distances from w. It's going to pull out all my successes. I'm sorry, I'm going to put there the number of successes. I'm going to pull out of n the number of trials. And then also I'm going to find, well, what will be the estimated proportion of successes? So I take good divided by good with respect to the w and n data frames and round to 4 decimal places. And this is what I get. So in 18 yards, there were 2 successes out of 3 trials. 2 divided by 3 is about 0.67. I feel sorry for that place kicker that missed that one place kick. 19 yards, hey, 7 out of 7. 20 yards, 776 successes out of 789 trials. Why are there so many trials at 20 yards? Because 20-yard place kicks, I screwed that up. Let me restate that. PATs, point after touchdowns, are usually at 20 yards. And since there's a lot of touchdowns that are scored in football, that's why you see so many place kicks at that distance. At 21 yards, there was 19 successes out of 20 trials. So now we have a binomial format to our data. To estimate the model in that format, I again use the GLM function. And I basically make 2 changes to my code. Now instead of putting the good variable, now I put success divided by trial. So essentially it's kind of like the proportion of successes. My explanatory variable is distance. And then I need to tell R, well, how many trials are there per row in my data frame. So I say weight each row by the number of trials. Everything else remains the same. Put the results in mod.fit.bin for the lack of a better name. And this is what I get. Beta hat 0, beta hat 1 are exactly the same as before. My stator errors are exactly the same. My z-test here, or what you'll see is my wall test is exactly the same as before. It doesn't matter what format your data is, you'll still get the same estimated model. Now do note that there will be some differences in other places in the output. And we will discuss in Chapter 5 why those differences occur. Okay? But this table here will be exactly the same. Are there any questions?
Can we see which model is better? We can compare, right? Because they are the same.
They're the same model, so it wouldn't make sense to compare. Sorry to put that bluntly. They're the same model, okay? The binomial format, though, does have some advantages, and we will see that in Chapter 5. Basically, the advantages are when you're trying to assess how well your model fits the data. So the bottom of page 27. So back in section 1.2, we had a Bernoulli response, where we had we had essentially a binomial response. You know, our columns were usually success and failure. And then for our explanatory variable, essentially that was just a binary explanatory variable. You know, like with the polio example, we had vaccine or placebo. Well, you can estimate a logistic regression model to that data as well. So the treatment, placebo or vaccine, is essentially like the change variable that we had with the place-kicking data set. Let's say maybe 1 for vaccine, 0 for placebo. And you can estimate a logistic regression model to that. I've actually given that as a test problem in the past. And unfortunately, some students have had difficulty with it. So because of that, one little change I've made this semester is I've put in the homework for Chapter 2 an example of how to work with that. So please make sure that you do that. Who knows, maybe we'll appear on the next test. Are there any questions? Okay, well, let's talk about hypothesis tests for our regression parameters. Our regression parameters are betas. And it's very important for us to know, well, is a beta equal to 0 or not? Because look what happens in this particular model. If, let's say, this particular explanatory variable, the rth explanatory variable, just to be general, what happens if that beta sub r is equal to 0? Well, what that's basically saying is that x sub r is not going to change anything with regards to the probability of success. So we will often want to do a hypothesis test then for beta sub r. Is it equal to 0 or not? And so here's our hypotheses. Beta r equals 0 versus beta r does not equal 0. Alternatively, you could represent the hypotheses in a model form. And sometimes it's better to do that because you could see better what the hypotheses are representing. So, in general, again, let's say that this is my model. I have p explanatory variables in it. I have p plus 1 total parameters. My null hypothesis model, basically, notice you do not see beta sub r. You do not see x sub r because beta r is equal to 0. My alternative hypothesis model contains that in there. But what's especially important for you to notice is the similarities between these two models. For example, x1 is in both models. xp is in both models. So essentially what this test is doing is saying, given I have all these other variables in my model, let's just do a test for beta sub r. Okay? So it's like a condition on, I have all these other variables in my model, let's test this one particular parameter and its corresponding variable then. So because of that, often there's another set of terminology that's used with this. So my null hypothesis model is often referred to as my reduced model. Because notice how it's smaller than what my alternative hypothesis model, which is often referred to as, what do I use as my terminology, a full model. Sometimes people will call it a complete model. So we have a reduced versus full model. And this is a fundamental aspect of comparing models. You compare a smaller model to a bigger model, where that smaller model is essentially a subset of the bigger model. And you look to see, well, which one's better? Well, how can we do this test? Well, we can use a wall test. That's what we were alluding to before. Where my walled statistic is essentially this. Let's call it z sub 0. Beta hat sub r minus the hypothesized value for beta sub r, which is 0, divided by the estimated square root of the variance for beta hat sub r. The reason why that beta and the hat are in blue is because for some reason in my notes, my hat got extended over to where you see the r. And perhaps I'm just a little picky. I was disappointed about that when I was going through my lecture notes today, so I changed it. So now that you calculate the test statistic, then how do you make a decision of should you reject or not reject HO? Well, it goes back to your fundamentals from your first stat course. So let's say here's my standard normal distribution centered at 0. Now, if I observe a value of z0 out here, would that be reasonable to have happen if the null hypothesis was true, or would it be unusual? Unusual, because the probability of being out there is so small. If I were to observe a z0 here, would that be unusual, or would that be maybe expected? Kind of expected, because the probability of being right about there is large. And so all we do with hypothesis testing, such as this, is we look at if the null hypothesis is true, is when I'm observing unusual or not. And how we make that judgment is we put some critical values on our distribution. Here's my 1 minus alpha divided by 2 quantile from a standard normal. Here is my alpha quantile from a standard normal. So if alpha was, alpha divided by 2. So if alpha was 0.05, then this would be negative 1.96 and a positive 1.96. And so if my absolute value of my test statistic is greater than, let's say, the upper bound there, then I reject. Otherwise, I don't reject. My p-value, again, based upon what you learned in your first stat course, would be just simply 2 times the probability that a random variable z with a standard normal distribution is greater than the absolute value of z sub 0. Again, these tests are automatically given to you by using the summary mod.fit. code that we used before. And we're almost done here. Now, you know, this word wall, hopefully you're starting to feel a little bit scared about whenever wall comes up, because you know that there are issues with wall. And wall tests, which is this is, and wall confidence intervals are good. You know, typically in most situations you're always going to be able to calculate them doing max likelihood estimation. The problem is that they are not always the best procedures to use. And that is the case here. And so because of that, we will focus more so on using likelihood ratio tests for this hypothesis test. Okay, we are out of time here. Are there any questions? Yes?
Is the project due by noon on Thursday?
It's due at class time on Thursday. But you can turn it in by noon on Thursday too. I'll still accept it. Any other questions? Okay, that's it for today.